So, we looked at the overviews of the three important welding processes that are generally used in automotive industry. The first we looked at resistance spot welding, and then we moved on to laser beam welding, and finally we looked at some of the advances that are so far made in gas metal arc welding, which actually makes this process very attractive for welding of some of the new generation advanced and steels, not only welding and also for brazing applications. And so we will move on to the welding metallurgy, the third chapter, how these welding processes affect the carefully designed microstructures of advanced and steels, and we will also look at the effect of alloying elements that we add, and what are the behaviors of these alloying elements when we apply weld thermal cycle. So, in the previous lectures I talked about the microstructure of advanced and steels and how we stabilize this microstructure by applying a complex heat treatment and adding the alloying elements which are not generally present in the amount we add in advanced and steel in conventional steels. Trip steel microstructure, base material microstructure is given in this slide. So, as we have seen that trip steel contains typically three phases, ferrite or you can say magnetic ferrite, and then some amount of retained austenite. So, generally this retained austenite gives the superior properties of the strip steel. When this retained austenite transforms to martensite upon loading, you get enhanced plasticity as well as the increasing strength. And of course, these alloys, trip steel also contains the increased amount of manganese as well as zinc and aluminum. They also give solid solution strengthening. So, now we will see how a weld thermal cycle affect this microstructure. What are the behaviors of the alloying elements during welding. So, as I explained in the previous lectures, the trip steel contains the alloying elements of higher amount of either aluminum or silicon or some amount of phosphorus, apart from the carbon and manganese. So, generally trip steels can be classified into two important grades in conventional trip steels. So, one is the aluminum based trip, the other one is the silicon based trip steel. In aluminum based trip steel we stabilize retained austenite by adding aluminum in the range of not more than 1.2. There is a metallurgical reason why we won't add more than 1.2, that will come to we will discuss later, but then typically it is about 1% aluminum. Okay. Apart from aluminum we also have about 0.2% carbon and manganese of 1.5 to say not more than 1.8 in a conventional trip steel, and we reduce silicon in aluminum steel. Silicon is in conventional level in 0.3 to 0.4, and the phosphorus it is kept as a level which is actually considered as a safe in weld, safe to weld. In silicon based strip steels we replace aluminum with silicon. The silicon generally is added in around 1.58%, and generally the carbon and manganese remain the same. So, there are positives and negatives in terms of metallurgical aspects by adding either aluminum or silicon. Silicon based strip steels are conventionally developed, and then the commercialization was also started by silicon based strip steels, but there are issues with the addition of silicon because silicon forms surface oxides. So, the galvanizability became improper, and there was a severe effect of the silicon oxide formation, surface oxide formation, and the adherence of zinc coating onto the surface. Because of that, the addition of silicon was not seen as a good alternative to generate trip steel. So, there was some work to replace silicon with some other alloying element, and one of the development was to replace silicon with aluminum, and therefore the aluminum based strip steel were also came into picture. So, aluminum is also effective as I already explained in suppressing cementite formation, but aluminum is very poor solid solution strengthener. compared to silicon. So silicon is a very effective solid solution strengthener in ferrite, whereas aluminum solid solution strengthening is not that effective compared to silicon. Naturally, the amount of aluminum is added is sufficient for stabilizing retained austenite, but strength cannot be achieved to higher levels as compared with the silicon based strip steel. So the increased amount of phosphorus is also added in aluminum based strip steel to compensate the strength, the solid solution strength loss by the addition of aluminum. And we will see the effect of each individual alloying elements during welding in subsequent slides, subsequent lectures. So right now we can assume that we can make strip steel with two different composition ranges. So one is aluminum based strip steel and the other one is silicon based strip steel. And aluminum based strip steel we stabilize retained austenite by adding about 1% of aluminum, and silicon based strip steel we add about 1.5% of silicon to stabilize retained austenite in both steels. So even though these steels chemistries are entirely different, apart from common manganese, you see the amount of silicon and aluminum present in these two steels are slightly different. What you have, it is in both the cases similar. Where we have ferrite and carbide free bainite or bainitic ferrite and retained austenite which is varying from say 10 to 12% of retained austenite, not more than 15%, because the microstructure what you generate is more or less similar. But when you look at the phase diagrams of these two steels, and you see two different entirely two different phase diagrams. For example, the left side of the slide you see in an aluminum based strip steel, and the right side you have a silicon based strip steel. So if you look at the aluminum based strip steel phase diagrams, so these are all the quasi binary phase diagrams. So where we plot an iron carbon diagram with an influence of the other alloying elements. And if you look at by adding 1.1% aluminum, so the aluminum being a very strong ferrite stabilizer, and we enlarge the delta ferrite lobe over here, and then when you have an higher amount of aluminum, your delta ferrite is stabilized to much lower temperature because the aluminum is very strong, the alpha stabilizer. And this can have a significant influence on the weld microstructure, because when you have a solidification from the liquid weld pool to lower temperatures, and because of the partitioning of aluminum, it can lead to a stabilization of delta ferrite, and that can happen in a weld metal. Whereas compared to aluminum based strip steel, silicon based strip steel show the conventional the iron carbon phase diagram, even though if we add the 1.5% of silicon and manganese and the other alloying elements, the phase diagram looks more or less at least the phase fields look similar to in a conventional iron carbon diagram, because silicon is not that effective in promoting any phase when it is in a very low amount, whereas in aluminum can have a significant effect of enlarging the delta ferrite and austenite lobe, what is called intracritical lobe. So even though the mechanical properties, the microstructure may appear similar, in terms of the microstructure evolution, and these two steels when they cooled continuously from the melting point, and you may expect a different stabilization, the microstructure stabilization, microstructure evolution mechanism can be entirely different in these two steels because of the change in the phase fields in the phase diagram, what you see over here in this slide. So we will have to now see an individual cases, and if you apply a typical weld thermal cycle and how the microstructure evolution takes place, even though your base microstructure may appear similar, the weld microstructure can entirely be different based on its individual composition. So what does welding do to in steel or for that matter it's any material. So if you look at the macroscopic effect, the weld, if you look at it, and then so you would see two distinctive effects. So one is so when you do weld and you also have an anisotropic thermal expansion. Because you have a varying amount of phases. In this case, we have a trip steel, for example, you have 3 phases, ferrite and carbide fibinite and retin austenite, and the thermal expansion of these 3 phases can be different entirely. When you have a base microstructure, when you are heating up to higher temperature, and each phase can expand and contract when you are doing heating and cooling entirely differently. So you may have inhomogeneous strain development when you apply a weld thermal cycle. And apart from that, you also have the strains that are evolving due to the phase transformations. So these are all added together and then can lead to severe residual stress development in and around the weld. So the first effect you see macroscopically is the evolution of residual stress, and this stress can lead to distortion of the plates. So we are not going to in detail into the residual stress evolution and the distortion. So we can assume that when you are welding, and because of inhomogeneous strain development in various levels, mainly in 3 levels, in a macroscopic level and in a phase level, in a grain level, as well as in a crystal level. So you may expect a strain development, and this strain can lead to distortion. Apart from the macroscopic strain effect, of course, you also have a temperature effect. So when you apply in a weld thermal cycle, and in and around the weld regions also heated up to various peak temperatures, and they are heated up to melting point. For example, if you have a plate, it's a welded plate, so we have the weld at the middle. So a bead-on plate weld is made with GMAW in this case. And so you have a weld center line. So weld center line is over here. So the weld regions, so the temperature reached is much higher than the melting point. So you form a molten pool, and if you move away from the weld center line, your peak temperature decreases as a function of distance from the weld center line. So the peak temperature reached in and around the fusion boundary will be close to melting point, but will be less than the melting point at the fusion boundary. And when you move away from the fusion boundary, the temperature decreases significantly. So if you look at the peak temperature, based on from the phase diagram, you can look at it. So when the temperature reached above the A3 line, recall the lectures, my lectures on the phase diagram. So when the temperature reaches above the A3 temperatures, so you have a complete austenitization, and then the heating and cooling rate would dictate the amount of austenite formed. Suppose if you have a temperature reached much higher, even if with a very fast heating rate, so you may have a fully austenitic microstructure, and subsequently you can cool it back to fully monazite microstructure. So if you move away, obviously the temperature, peak temperature reached, it's also can also fall in between the intercritical annealing regions. So where you have regions in heat affected zone, say for example somewhere over here, and you may also have a temperature reached to an intercritical temperatures, and you may also have intercritical annealing treatment, for example. And when you have a temperature reached below A1 temperature, where you may not see any phase transformations, but there could be some other effects. For example, if you have martensitic microstructure, say in a dual phase steel, you may also temper the martensite, and when the temperature reached below the A1 temperature. And in a trip steel, and you may also have some effect in the retained austenite, because retained austenite is not stable when you heat it up to higher temperatures. Okay, so we will see in that effect. So based on the welding process, the heating and cooling rate can also change. So typically, say if you look at the various regions, so now if you look at time temperature graph, say for example a region somewhere over here, where the peak temperature reached say about 1500 Kelvin, somewhere around say 1200 degrees centigrade. So the peak temperature So if reached to 1200 degrees centigrade at this point, so you will have a heating to 1200 degrees centigrade and subsequently so cool to room temperature. So say for example about 1200 degrees centigrade. If you move away from the well center line, this is somewhere over here. So the peak temperature may be reached to say 1000 degrees centigrade. So then you will have a curve something like that at that point. And similarly, if you move away elsewhere, so you may also go to the intercritical region where the temperature can go up to say 800 degrees centigrade. And so where a peak temperature reached, say this will be 1000 if you say, and if this will be say 800 degrees centigrade where you will have intercritical regions. And if you move further away, so further away the temperature may reach say 600 degrees centigrade, and you will have a thermal cycle developed. At this point in this manner. So the heating and cooling rate is determined by your the material thickness and the heat transfer of your material, your the local conditions, as well as the heat source characteristics. So generally, if you have the material thickness for a given material thickness, the resistance spot welding gives the maximum heating and cooling rates, where the heating and cooling rates can go in RSW the order of 1000 centigrade per second, whereas in laser beam welding, so you can go up to a few hundreds of somewhere between say 500 to 1000. So whereas in GTAW or GMAW, the cooling rates can be controlled in the order of say 100 Kelvin per second, and the heating and cooling rate can be controlled in the order of 100 Kelvin per second. So if you look at it in RSW, the resistance spot welding gives the maximum heating and cooling rate, as well as the temperature gradients is very steep in RSW, and subsequently in GMAW welding. So imagine now, if you are heating up in 1000 Kelvin per second rapidly to an oscillation temperature and cool back, and you can expect a severe heterogeneity in terms of microstructural development at various regions, and the cooling rates will dictate that when you have fully austenitic microstructure, you will end up getting matacitic microstructure. And similarly, when the temperature reaches to intercritical region, and you will not form a fully austenitic microstructure, you will have the two-phase microstructure wherein your austenite can also be enriched in carbon, similar to what we looked at when we looked at the intercritical annealing treatment. And based on the temperatures reached, you may also have a gradient in the enrichment of austenite. For example, regions reached where the temperature reached to just below an AC 3, then you may have the maximum amount of austenite. So you may not enrich the austenite significantly, whereas in the regions just above the AC3, AC1, and you may have a highly enriched austenite. And again, so there will be an interplay between the temperature as well as the partitioning and the amount of austenite you form, can lead to an increased amount of retained austenite stabilization when the peak temperature reached to an intercritical annealing temperature during welding. Of course, when the temperature reached to fully austenitic region, and you have the fully austenitic microstructure where so you will not have a benefit of carbon partitioning when the temperature reached to intercritical annealing temperature. So from this the complex thermal cycle you expect during welding, and you may also expect a very complex microstructure that are generated after welding. So whatever microstructure we have in the base material, a beautiful microstructure generated from the complex thermomechanical treatment as well as the adding alloying elements, now weld it has its own thermal cycle. Okay, so when you are applying such a weld thermal cycle, so you may expect a very heterogeneous microstructure generated after welding. So now we will have to understand from the metallurgical point of view how this Weld thermal cycle is going to influence the microstructure evolution, and from this understanding, and we can also mitigate this Weld thermal cycle. In last chapter we are going to look at how we can engineer these thermal cycles so that we can minimize the damage the Weld thermal cycle does to the carefully designed microstructure. So this is an overview of a weld made using a GTAW, a gas tungsten arc welding, other variant. So we just applied a simple weld thermal cycle, and then if you look at the weld zone, so this is the fusion boundary. So what you see over here, and if you look at the microstructure of say this is an silicon based strip steel. After a GTA weld, simple bead-on plate weld, you see a columnar solidification, and you also see in the center line equiaxed grinds, but grind mode is not visible, but so it becomes equiaxed. And then you also see these black dots that are actually inclusions of non-metallics. Okay. And you also see the heat affected zone. You see the coarse grain heat affect zone. This is completely martensitic microstructure, where the temperature reached here is fully austenitic, and then subsequently when you cool it, and then it becomes fully martensitic. And weld zone is, if you look at it closely, in slightly higher magnifications in the same steel in high silicon weld. You see this is the fusion boundary, the heat affected zone is fully martensitic, and with the grind boundaries are decorated again with the non-metallic inclusions. And so this is not an ideal weld condition when we made, and this is show that when you use a conventional weld thermal cycle and you have an severe inclusion formation in high silicon steel weld, and we will see the two major effects of a weld thermal cycle here. Now if you make a simple welding case, so you will have formation of the inclusions, these, and then a complete martensitic microstructure with when you have a grind boundary melting, and you may also have an inclusions that are formed along the grind boundaries in the coarse grained heat affected zone. And this is in a high silicon steel case. When you have an so when in a high aluminum case, and the weld showing in the microstructure, if you look at the high aluminum weld, so what you see over here, apart from the inclusion formation, inclusions are non-metallic inclusions in the fusion zone. So this is your fusion boundary. And apart from the inclusion, you also see a distinct layer of at the fusion boundary, a stabilization of a phase, and in this case, so this is a delta ferrite. Okay. So recall the aluminum iron carbon phase diagram with the influence of aluminum. So when I was showing the phase fields, and we showed that by addition of say 1.1% weight percent of aluminum, so your delta ferrite is also stabilized to much lower temperature. So what we are seeing over here, the effect of addition of aluminum, and aluminum can lead to stabilization of delta ferrite in the fusion boundary because of the partitioning of aluminum during solidification to the solidifying delta ferrite. So we will see how these happen, the metallurgical reasons behind this stabilization. So you need to see, you can understand from this microstructure the effect of alloying elements very clearly. So when you add higher amount of silicon and aluminum, and both aluminum and silicon are highly oxidizing. So the aluminum readily forms oxides, and these oxides no, it can form at very high temperatures, above even over melting point. The moment you have the oxide formation, you may also have an enrichment of volatile elements onto this oxide formation, and can lead to the formation of non-metallic inclusions. So by increasing the aluminum silicon concentration, which are needed to stabilize retained austenite, we may also form non-metallic inclusions invariably in the well zone. In aluminum based strip steel, apart from the inclusion formation, and we may also have a soft zone of delta ferrite that can be stabilized in the fusion boundary. Okay. So we will see in detail about the mechanism of inclusion formation and the aluminum partitioning, behavior of aluminum partitioning in subsequent classes, and then we will see the effect of the other alloying elements, for example phosphorus and boron in advanced heights and steels, how the welding microstructure can be influenced by the partitioning of these alloying elements. So first we will begin with the addition of silicon aluminum. So as I already showed in these two microstructure, because of the highly oxidizing nature of these aluminum and silicon, the both elements form oxide inclusions, and subsequently they may also attract other alloying elements, and then leading to the formation of non-metallic inclusions. And the aluminum, because of the affinity to delta ferrite during solidification, and upon reaching critical limit, it can also stabilize on the fusion boundaries upon solidification. So the delta ferrite, you can also very clearly see that the stabilization of delta ferrite at the fusion boundary. So the having a delta ferrite at the fusion boundary sandwiched between the martensitic base microstructure is extremely vulnerable, because the delta ferrite is considered softer than the adjoining the matrix, which is fully martensitic in this case. And if you have a soft delta ferrite region in between martensitic microstructure, so obviously when you are loading this structure, either in tensile or shear load, your load will be strain will be partitioning to the fusion boundary, and you expect a failure of the fusion boundary when you are loading. So so far what we have seen here in these classes, so we looked at the welding metallurgy, the very basics of welding metallurgy in advanced heights and steels. So how a typical weld thermal cycle evolved during welding. So we will also look at the chemistries of strip steel, and the addition of silicon aluminum is it's very needed to stabilize it in austenite. But when you have silicon and aluminum present in the weld pool, because of the highly oxidizing nature of these elements, and you may form a inclusion, non-metallic inclusions, and the partitioning behavior of aluminum to the solidifying phase can stabilize the unwarranted phases at the fusion boundaries. So we look at in detail the role of these alloying elements on the evolution of microstructure, and how the weld thermal cycle can influence the microstructure evolution with the presence of these alloying elements in subsequent lectures. Thank you.